So now we're going to dig into the, let's see. Now why? Share is right. But I can't see myself up there. There we go. So I can see what I'm doing. Yep. Okay. We can take a look at the periodic table and how it's structured. You can get a whole lot of information from the periodic table if you know how it's built. Not just go inside each little square. I mean, there's a pattern to the way things are organized. I didn't mean to do that. That's okay. All right, these are the topics we're going to cover, and I never stop there. It's just an outline for whoever wants to use it. The periodic table is constructed based upon how we build atoms. But it didn't just happen overnight. It took a lot of effort, a lot of false starts, you know, chasing their own cars. But we can go back to John Dalton as the first coherent theory about what elements are made of. And these icons or schematics that we see across the top there are representative of what each of those persons was dealing with or created themselves in terms of how an atom looks. What is an atom? Which is basically the element, because elements are composed of a single type of atom. John Dalton in the early 19th century came up with the atomic theory, actually. And what he said was that atoms, let's see, just a second. Yeah, let's get my copy out. Here we go. Atoms, John Dalton said, are the fundamental unit of elements. They're very small, and he actually borrowed this concept from the ancient Greeks. The Greeks believed that all matter was composed of an elementary particle they called the atom. And they called it the atom because in Greek, tomos means to cut. And a prefix of a means not. So you can't cut it any further. It's the simplest particle of matter. The problem with the ancient Greeks was they said all matter is made up of the same type of atom. So there they painted themselves into a corner because now they have to explain why we have such different types of matter. And they had identified 2 or 3 or 4 different elements at the time, and they had to explain why, if they're all different elements, how do you get the same atom to produce such different characteristics for each of the elements? So they came up with some pretty wild ideas, and one of them that seems to have stuck was the 4 essential, what do they call them? I forget the name for it, you know, earth, wind, air, and fire, right? Those four things. And they tried to use those to explain why this simple atom could account for all the different characteristics of the elements. So that's where John Dalton started. He started with, he said they were half right. Everything's made up of elementary particles, except that each atom in every element is different than the atoms in another element. So that's how he got around it. That's the fundamental difference. The problem is he didn't know that there was anything inside the atom. He thought it was just a ball, like a bag, a sack. And then we come to J.J. Thomson, who discovered the electrons. He said, okay, there are parts of the atom that are negatively charged. And this was in the beginning of the 20th century. And he said that because I've discovered these negative particles that they call the electrons, there must be positive charges in there also, because they knew that the atom was neutral. So you had to balance the charges in order to have a neutral atom. But he couldn't get a handle on those. So the model that he was proposing came to be known the plum pudding model. I don't know if that was his idea or if it was just somebody modeling it. Have you ever eaten plum pudding before? Okay. Well, you know, it's kind of, you know what a pudding is. Well, in plum pudding, you have these little pieces of plum scattered throughout the matrix. And that model says that those little pieces of plum scattered throughout are the electrons. And everything else is positively charged. The pudding is positive. So that balanced the charges. Well, not too long after that, Ernest Rutherford, who was another Englishman, said, that's just ridiculous. So he proposed another idea. His idea was the nuclear atom, where the positive and the negative charges were separated. And by that time, J.J. Thomson had, excuse me, yeah. J.J. Thomson had been able to determine the ratio of the mass of an electron to its charge. And that didn't tell you exactly what the mass of the electron was, but it gave you a sense of the fact that the electron was probably really small, had almost no mass. And Rutherford picked up on that idea, and he said, okay, if the electron has almost no mass, where's the mass, right? Is it in this pudding? He didn't think so. He thought that most of the mass was concentrated in a very small part of the atom called the nucleus. That's where the positive charges were, and that's where most of the mass is. So, and I think, let me see, I don't want to steal my own thunder. I guess I'm going to have to. Okay. So Rutherford proposed an experiment. By this time, at the beginning of the 20th century, radioactivity was all the rage, as they say. And various types of radiation have been identified. One was alpha radiation, one was beta, and another one was gamma. The alpha radiation was just a helium nucleus. It was a positively charged helium atom. Like that. That's basically what it was. Only it originated, they knew, from inside the atom. Researchers had determined that these particles, well, this is a particle, that's a particle, but this is radiation. Right, so these two are particles, but this one is like an electron. It's very, very light. What Rutherford wanted was something that was heavy. So he devised an experiment where he took these particles in a lead shielded device, So there's your radioactive material, and these alpha particles were streaming out of there. And of course, they were coming out at different angles. Okay. Well, what he wanted to do was shoot them at a very thin foil, something they could make really thin, just a few atoms thick, because he knew if it was too thick, then the alpha particles would not make it through. They'd be stopped. That had already been demonstrated. So he chose gold because he knew that gold could be hammered really thin, and it was easy to obtain the gold foil. So he set up gold foil out here. Right. There's the symbol for gold. And it was just 3 or 4 atoms thick. But he wanted to be sure that this beam was straight. So he set up 2 slits, and they were aligned in such a way that only the alpha particles that were going perfectly straight would make it through both of them. Right? If this one came in at an angle, it'd been stopped over there, stopped over there. So you got this stream of alpha particles, and they strike the gold foil. What Rutherford said was, if the plum pudding model is true, then most of this space, the mass of the atom is spread out so far that these alpha particles ought to go straight through and hit the detector right over here with no change of direction. But he said, if my model is true, the nuclear atom is true, then most of the density, most of the mass of the atom is in a nucleus. And whenever these particles strike the nucleus of the atom, several things could happen. If they hit head on, then the alpha particles will come straight back, and you'll detect them over here. That big circle is multiple detectors. If it hits a glancing blow, then you'll have some end up over here or over here. So he conducted his experiment, and sure enough, most of them ended up over here. But there are a few that struck off in odd directions, and some of them came straight back. That was confirmation that Rutherford's model was the correct one. And from that point on, the plum pudding model was dead. So now we have a nuclear atom. We know that the atom is not just a bag, and it's not a plum pudding, it's nuclear. The positive charges are in the nucleus, negative charges are in the space around the nucleus. Okay, that takes care of that much of it. And by the way, Rutherford got a Nobel Prize for this one. So the problem now is that we know that the atom is made up of these positive charged, very dense particles called protons. Right? We use the symbol like that for protons, and electrons. Right? That balances the charges. But the mass that's attributed to each of the elements cannot be accounted for fully by the number of protons. But this time we'd managed to determine the mass of each one of these. That story is too long to go into. But there was extra mass in there, and it couldn't be charged because we already accounted for the charges. So Rutherford's graduate student and later his research assistant's name was Chadwick. Rutherford gave him the job of figuring out what that was. And he discovered through his research that there were particles in there that were about the same mass as the proton, but with no charge. These are the neutrons. So now we know that the atom is made up of subatomic particles. It can be cut in protons, neutrons, and electrons. These other guys, Niels Bohr and Schrodinger, we'll cover them later. I think it's too much to get into right now. Let's get a little bit more information under our belts. Okay, so we have these subatomic particles, that we can use to build atoms. And there's the ratio of the charges and the masses. So we see that the electrons, protons, and neutrons really are pretty small, right? 10 to the minus 28th grams for an electron, 10 to the minus 24th grams for protons and neutrons. But notice, ratioed, the proton is 1,800 times as heavy as an electron, and the neutron is just slightly heavier. So sometimes I use the expression orders of magnitude. Have I explained that yet? Orders of magnitude, that's just powers of 10. So if the electron is on the order of 10 to the minus 28th grams, and the proton is on the order of 10 to the minus 24th grams, that's 4 orders of magnitude difference. Okay. Actually, the electron is almost 10 to the minus 27th, isn't it? Because the coefficient is 9, almost 10. So it'd be more accurate to say this. So it's 3 orders of magnitude in between 3 and 4. And as it turns out, that's right, because 3 orders of magnitude is 10 to the third, or 1,000 times. 4 orders of magnitude is 10,000. So it's between 1,000 and 10,000, and sure enough, it is 1,800. All right. So out of all this is just as a rehash of the story. We know that the nucleus is very small, very dense, and positively charged. It contains all the protons and all the neutrons. Okay, that begs the question. Everybody knows that like charges repel each other, correct? When you try to pack those positive charges from the protons into a small space, how do you keep them there, right? Are they trying to fly apart? Electrostatics says, yeah, there's a repulsive force. That's the job of the neutrons. The neutrons are there, and we can't go into a lot of detail, but the neutrons are there to stabilize the nucleus and to keep all those protons from flying apart. Okay, in a neutral atom, we've already said this in one form, this is another form. In an atom, the number of protons equals the number of electrons if the atom is neutral. There's no charge on it. That's just pure electrostatics. They have to balance the charges. Okay, when we write a chemical symbol for an element, I'm going to use a generic for this purpose. Just say we have the chemical symbol there, and I can use X because there's nothing on the periodic table, it's just X. There's an Xe, or a xenon, and there are 4 positions around that symbol that are reserved for information. The first one is Z. That position, if we put a number there, that position says what is the atomic number of the element, which is equal to the number of protons. Okay? And that is unique for every element. If you write a symbol, then it has a specific Z, a specific number for that element. For instance, well, hydrogen. Hydrogen would be 1. It has 1 proton, that's it. And if you say my element has 1 proton only, you automatically know that's hydrogen. So they're Siamese twins. How many protons? That's the element. This number, this position designated by A, is equal to the mass number. And that's equal to the number of protons plus the number of neutrons. Okay, it's always a whole number, the mass number. If you have this number and that number, then you can calculate the number of neutrons You just subtract this number from that one, right? There's that one. Subtract it away. You have the number of neutrons. Okay, we've come that far. This position is reserved right here for charge. So if there's a charge on that atom, it is an ion. So how would you get a neutral atom to be charged? You can't change that, right? You can't change the positives, because if you do that, you got a different element, right? So the only way that you can get an ion from a neutral atom is to change the number of electrons. If you take electrons away from a balanced neutral atom, what charge are you left with? It's not a trick question, right? Only positives, right? If you take away some negatives, you have an excess of positives. That gives you a positive charge. It could be 1, it could be 2, it could be 3, however many, depending on how many electrons you remove. And that's generally characteristic of metals. They tend to lose electrons. If we add electrons, then the balance is shifted toward the negative, and you get a minus charge on the atom, which makes it a negative ion. Okay? All right. Those negative ions tend to be characteristic of nonmetals. Right? We haven't discussed the chart as to where things are, so bear with me. One more position. This is the number of atoms. If there's nothing there, that means there's 1. Right? We're not going to be redundant. We don't put a 1 there. If the symbol's there and there's nothing here, there's got to be at least 1. Okay? Only if you have 2, 3, or more do you put it down there. Now, why would we do that? Well, remember the handout I gave you on which ones to learn, the symbols to learn? Some of them have blue backgrounds to them. Those are called diatomic elements. And when you find them in nature, those elements like hydrogen will actually have 2 atoms attached, like that. Or if you have oxygen, it'll have 2. Or nitrogen, it'll have 2. Or fluorine, it'll have 2. Or chlorine, I might as well give you all of them. Bromine, iodine, they're all diatomic elements at 1 atmosphere pressure and room temperature. Okay, so that tells us that in this, whatever this formula is, there are 2 atoms of hydrogen attached to one another. That's what that position is for. And when you write more complicated compounds like water, you'll have 2 atoms of hydrogen and 1 atom of oxygen in that formula. Okay. Now, when we get into chemistry, this is what we use when we really want to provide information about the atom itself. We have values here and here. Most of our encounters with chemistry in this class, after we get past this section, we won't bother putting those values in there because we won't need them. We only need them if we're going to talk about the inside of the atom. Okay. So if we wrote sodium, here's one possibility. Sodium has 11 protons. No other element has 11 protons only in its nucleus, just sodium. And the mass number is 23. So how many neutrons do we have? Try 12, right? 23 minus 11, 12 neutrons in that particular atom. Okay. I think we covered this before. By definition, an element is any pure substance that can't be broken down further into simpler substances by chemical means. In other words, you can't shock it with electricity or heat it up high enough or hit it with a beam of light and break it apart. That's an element. And in that case, that pure element has atoms in it that are all the same, at least with respect to the number of protons. Okay? The number of protons are the same for every element, for every atom in that element. And that's why they have the same chemical properties. There's more to it than that, but for now, that's good enough. Okay. The thing that can vary from atom to atom of the same element is the number of neutrons. Right? We can change the number of neutrons in the nucleus of the atoms of an element, and it will still have the same chemical properties because it has the same number of protons. Now, I'll give you a little teaser. The atom, yes, is made up of protons, neutrons, and electrons. But the chemistry of the atom is due to the electrons. Think about it. How do we know something reacts? It has to come close to some other element, doesn't it? Right. You can't just sit up there by itself and say something about it. Well, we could, but we don't know it until we try to react it with something. And when two atoms approach one another, what do they see first? They see electrons. So the chemistry between two atoms of different elements, or of the same elements, is due to their electrons. And of course, if they're neutral, that's the same number as the protons. So the chemistry is due to the electrons, and the isotopes of different of the same element, isotopes are due to the change in number of neutrons. So you can change the number of neutrons and you got the same element because you have the same number of protons. So most elements in nature exist in different isotopic forms. Some of them, most of them have a vast majority of one particular type, like that sodium. That's the most common isotope for sodium. But sodium can have another one, which is not so common. Right? It's missing one neutron. Okay. Most of them are like that. There are only a couple that have a substantial number of two or more isotopes in the mix, in the natural occurrence. Chlorine's one of them. It's about 50-50, this isotope and that isotope. There's another example, silicon. If we say, I have an element that has 14 protons, right? Can you tell me which element it is? Look on the periodic table. You see those letters, the numbers in red on the lower left-hand side of each square? That's the atomic number. So all you have to do is follow it. It gets bigger from left to right and top to bottom. So you just follow along until you find one that has 14 in it. There it is, 14 over there. 1, 2, 3, 4, 5 rows to the left, 5 columns to the left, down below carbon. Yes, 14 is its atomic number, which is the number of protons. We know that's silicon. But silicon, it can exist, as most elements do, in different isotopic forms. And let's see, I'm getting a glare. Not to get close. The lights are not cooperating. Most most of the isotopes of silicon are the one on the left, silicon 28. And if we write it out in prose, not symbolic form, we would write like that. That's silicon 28. Okay. Let's see. What if we have this element? Let's see. Let's remove some of the clutter. We have this unknown element, but we're given this information. It has 23. Its atomic number is 23, which means what? 23 protons. And it has 28 neutrons. Okay. What's the mass number? Right, 51. Just add them up. What's the element? Go to the periodic table, look for 23. You find it? Okay. Do you know what that symbol means? That's an easy one. V for vanadium. So the symbol is V, and it has that for its atomic number and this for the mass number. Okay. There we go. Now, here's where students get confused. If you're not already confused. The mass number is always a whole number, and it's the summation of the number of protons and the number of neutrons. But the atomic mass, not the mass number, but the atomic mass, is a weighted average of the masses of all the naturally occurring isotopes of that element. This is actually a more useful number if we know the atomic mass. And that number is a fractional number. It's always a fractional number. And on that periodic table, it's in the upper left-hand corner of each of the squares. Now, how do we arrive at that? First, we need to know the relative abundance of each of the isotopes, at least the important ones. And then we need to know what is the atomic mass of each one of those isotopes. Now, you might think that the atomic mass of each of the isotopes should be a whole number. And we may use that to help us calculate, but in fact, there's only one isotope in the periodic table that's accepted as a whole number. And that's, by convention, this isotope of carbon is equal to atomic mass units for that one atom. It's fixed. We need a reference point, and that's carbon. Carbon 12 is our reference point. It's accepted as exactly 12 atomic mass units. Everything else is ratioed to that one. So all the other isotopes that you can isolate from the periodic table will have fractional values. They'll be ratioed to this. Now, if we want to calculate the atomic mass, the atomic mass of naturally occurring carbon and take into account all its isotopes, we need to think of it in terms of like you calculate your GPA, right? That's a weighted average, isn't it? Now, if you take a course that's only worth 1 credit and you get an A in that course, it doesn't have as much weight as a course that has 4 credits and you get an A in that one, right? It's a weighted average. So you say, all right, if this one is 1 credit times an A, which would be 4 points, and this one is 4 credits, times an A, which is, excuse me, times 4. And this one's times 4. That's 4, and this is 16. Right? So your weighted average then would be 20 divided by total number over here, which is 5. Well, look at there. Of course, it had to come out 4 because both of these are 4s. But we could change that. Let's do that. Let's change it. Let's say you only get a B in this class and it's got 1 credit. So 3 plus 16 is 19. Again, divided by 5 credits total. What's 5 and a 19? 3. 5 and 4 is 8. 3.8. So your GPA with those 2 courses would be 3.8. It's a weighted average. So what I'm trying to say is isotopes that are higher in percentage contribute more mass to the total. So if carbon is 98.89% of all the naturally occurring carbon, then the value that's reported for the atomic mass in the periodic table should be pretty close to 12, right? Because that isotope is 12. But it won't be exactly 12 because we've got one that's a percentage, 1% or more of 13. And then carbon 14 doesn't count. Why? 2 reasons. First, it's really small, 0.01%, plus it's radioactive, so it doesn't hang around for very long. So if we do our calculations, how would we do that? Well, if we say this isotope is 12 atomic mass units, then this time, what is its abundance? 98.89%. It's better to use the fractional equivalent. What's the fractional equivalent of a percent? Divide 100 into it. Right. So this will be times 0.9889. That's a value. And then we have 13 atomic mass units times its percent, which is 1.11. All right, yeah. And then we get a value here and a value here, and we add them together. That's their weighted average atomic mass. Okay. Did I lose anybody? Do you do this kind of stuff in math class? No? Okay. It's brand new. But you understand the operations, I hope. This is the contribution of that isotope to the total. This is the contribution of that isotope to the total. And this is the total. And the total on the periodic table, get that glare again, is 12.0111. Right, so when you do that math, atomic mass unit is the average, the weighted average atomic mass for carbon. And periodically, these values are updated by people that do this for a living. Now, why should we care? Well, if we're conducting a chemical reaction and we need to know to complete the analysis and to do any calculations with it, this doesn't help us at all because our reaction was conducted with naturally occurring elements. And they're going to be a mix of isotopes, right? We don't have the equipment or the desire to separate those isotopes before we do the reaction. So by knowing this value, we don't have to, because that tells us all we need to know about that naturally occurring mix of isotopes. We can do our chemistry. All right. So this is now we didn't actually define an atomic mass unit We just said this is the standard. So one atomic mass unit is approximately equal to one proton. Not exactly, but it's close. But atomic mass units, while useful in a theoretical discussion, they don't help us much when we're doing chemistry. We need another unit of measure. And I think that's where we're headed. Well, this particular exercise takes a different element with two different isotopes, one at 62.6% and the other one at 37.4%, and they have those atomic mass units for each atom. Then the average atomic mass is such and such, right? So we would go through that same procedure. Do I need to do that? I will if I need to. So we would take 186.956, 186.956 atomic mass units times its relative abundance, 6260. And then we take the other one, 184.953, and these are atomic mass units, 0.3740. Okay, let's do that one. So get out your calculator. 186.956, and then its relative abundance, 626. So this says its contribution to the weighted average is 117.034. Let's see. I'm limited to this number. There we go. Atomic mass unit contributed to the total. And this one, 184.953, is only 37%, which is 69.172. So the weighted average would be those two together. 186.207 atomic mass units. Okay. Did you sign in? Be sure and sign in. So now that we know this value, let's see. There it is. Can we identify the element from that value? Up to this point, we've only identified elements with the atomic number of protons. But as it turns out, this atomic mass is not unique, but close to unique for each of the elements also. So if you follow those down, and they get bigger from left to right, top to bottom. If you follow that one down and look for it, 186.207, you'll notice that they get bigger as we go. We can just keep getting bigger and then bigger and bigger and bigger. 186.207, here it is right here. Rhenium is the element. Now, you didn't have to memorize that one. There are a couple of places on the periodic table where the atomic masses are really close together. So in that case, you would need a tiebreaker of some kind. Let's see if I can find one. These are pretty close. Selenium and bromine. These are really close. Tellurium and iodine. There are a couple others in there. But most of the time, the atomic mass will also be an identifier for you if you need to find out what element it is. All right. Just a reality check. Elements that have different neutrons but the same number of protons are isotopes. Now, that's one thing that Dalton's atomic theory didn't account for. They didn't know about isotopes when he came up with that theory. He said that all atoms of the same element are identical, but they're not. We know that now. Okay, let's get to the periodic table. The periodic law simply says that when elements are arranged in order of their increasing atomic number, the elements with similar characteristics are located in the same groups. So what does that mean, practically speaking? Well, if we start off with, say, potassium, everybody in that group acts like potassium. It's an alkali metal. And we go from left, we start building atoms, we add a proton each time, and we go across. And once we get to this side, we're up to a noble gas. If we add another proton, 37, then we either start a new column, or we say, does it look like any of the other elements in our table? Well, as it turns out, 37 behaves chemically like these guys. So we instead of putting a new column, we just swing back around and put it in here. That's a period. And it comes from the idea, the concept of periodic motion. You ever heard of periodic motion? Nobody's had physics? Okay. Periodic motion. Think of a pendulum clock. Right? What does a pendulum and a clock do? Well, it moves, but it doesn't go anywhere, right? It just goes back and forth. And if it starts off here and goes back here and then back up to here, that's one period. Over that period, it comes down, it goes back to the same spot. So we can think of periodic table in those terms. If we go down a row, which is called a period, to the end, and we go one further, then we don't need another column because we've got one already laid out back on the other end. So we start the period over again with another period. We go down, happens again. That's chemical periodic motion, I guess you would call it. And the table that we build from it is the periodic table. Now, when let me see. Now let's see him on thunder again. Yeah, okay, we do. We do have some information here on that. All right, so the periodic table, like I said before, it didn't just come fully formed out of some guy's brain. It was developed over many years, and one of the first scientists who recognized these similarities in behavior of the elements was Johann Dobereiner. Obviously, he was a German. And he grouped elements into threes that have similar chemical and physical properties. He called them triads. And he left it at that. He didn't take it any further. Meyer came along and he built a table with elements that were known at that time. We didn't know all of them, but the ones that he did do, he grouped those into a tabular form and put them together in groups of elements that behave similarly. And by the 1870s, 41 years later, more elements had been discovered. So he had more than just a triad, and he put those elements together. And what he said was, he introduced this concept of valency. He called valency of an element is an expression of its chemical behavior, and elements that have the same valency behave the same way. Now, at that time, they didn't know what valency really meant. We know now it means how many electrons are available for reaction. And we'll come back to that. We'll circle back to that one, as the White House press secretaries are known to say. The real advance in the periodic table was presented by Dmitry Mendeleev, Russian. He was a school teacher, and he was interested in the way extending an understanding of the way elements behaved and grouped them together and put them in a table. In fact, his table, the groups on his first table were left to right, and the periods were up and down. That was his first publication. His second publication, he rotated it 90 degrees. That worked better. But Mendeleev gets most of the credit for the periodic table, primarily because the way he arranged them, and he arranged them according to behavior and physical and chemical behavior. And if he had, and all they knew at that time was atomic weights. They didn't know about atomic numbers. They didn't know about protons then. All they were able to do was compare things based upon their weights. So when he came along and he was putting elements in their families, that's what they called them then. And he came to the next one to the right, and the next element that was the next heaviest didn't fit. It didn't have the same behavior as the family it was supposed to go in. So he skipped it. He went to the next family because he said, the behavior of my element is more like that family. So I'm going to put it in there, and there's an empty spot. He said, eventually we're going to find an element that fits that place, and it'll have this mass, and it'll have these chemical behaviors and physical properties. So he used his table to predict undiscovered elements. And sure enough, every one of them was found. So that's why Mendeleev gets most of the credit for the periodic table. He used it to predict the existence of elements that were yet undiscovered. It wasn't until the beginning of the 20th century that a young man named Henry Moseley, the Englishman, was doing work on pure elements, and he was looking at their X-ray spectra. So we'd take these elements and he'd fire X-rays at them, and then he would use a spectrograph to record the various emission lines that came off of them. And what he noticed was, if he focused on one of the lines, he could have used any one, but he focused on one of them. And he said, in my formula, as we go up in the elements from left to right, as they get bigger and bigger and bigger, he noticed that all he had to do was to predict the emission line for that new element was to change this one number in there. It was a whole number. We call it N. So he changed that number, and it would predict accurately the wavelength of the line that was characteristic for that element. And he called this the atomic number. Now, he didn't know at the time that what he was actually doing was saying the atomic number is the same as the number of protons. But that's what it became, that's what it was equivalent to. That whole number that he put in his equation was exactly the same number as the number of protons. Unfortunately, Henry Moseley was in his early 20s. And I don't remember if he was drafted or he volunteered, but he went off to World War I and never came back. So that was the end of his research career. Oops, excuse me. There we go. Okay, so this periodic table can be grouped into families. We call them groups now, but they used to be called families. And they all had similar chemical characteristics. Some of them have names. And when you fill out, when you work on that extra credit, right, the getting to know your periodic table, then one of the things you have to do is identify these families. So the alkali metals are the very first column on the left, right? Lithium, sodium, potassium, rubidium, cesium, and francium. They're all alkali metals, and they all have similar behavior. The next one over to the right are the alkaline earths, or the alkaline earth metals. Either one is fair. And then you go to the far right, you get the noble gases, right? All of those elements, helium, neon, argon, krypton, xenon, radon, those are all gases. And they're called noble gases because they don't react. They don't play with anybody. They're perfectly happy being separate individual atoms. Now, actually, some of the bigger ones, like krypton and xenon, have been forced into compounds, but for the most part, they like their single existence life. They don't marry. Halogens, the next ones to the left of the noble gases, are the halogens. Fluorine, chlorine, bromine, iodine, those are all halogens. And before the advent of LED lights, halogens were the best, the most efficient that you could use. Iodine in a halogen lamp would be more efficient at producing light than just an incandescent bulb or even a fluorescent. Well, I'll take that back. Fluorescents are pretty efficient. So, but if you go out to some parking lots now and they're still using the halogen bulbs, they'll have kind of an eerie greenish yellow light. Right? Things don't look right in those lights, but they do light up the parking lot. Chalcogens, those are the oxygen group. So if you find oxygen over there next to fluorine, then everybody in that group is a chalcogen. And that's based upon, that's a term that used to be used when you form a compound of an element. Most of the elements in the periodic table will form compounds with oxygen. They call them the calcs. So when you react them with oxygen, you get this compound, and that's why chalcogens are called that. It's based upon the behavior of oxygen. And the next to that one is nitrogen. That family is called the pnictogens. The P is silent. Now those parenthetical identifiers following each one are group labels, like 1A. And this is the old form. 1 is a Roman numeral. 2 for the alkaline earths is a Roman numeral. And they're useful, but notice that all the A's are these two first ones and these last 6. They're all Roman numeral A's. And you'll get down to the last one. They shouldn't put a 0 there. They should put an 8 there. These are the transition metals from here over to here. All those are transition metals, and they have B designation because they don't follow the trend very well. Have you had anatomy and physiology or a biology course? Anybody?
You take it now.
Okay. They'll talk about, if they say anything about chemistry at all, they'll talk about the octet. The octet is 8 electrons in the outermost shell. So these have 1 electron in the outermost shell. These have 2. These have 3, 4, 5, 6, 7, 8. The outermost shell. When you get 8, under certain conditions, then you have a complete shell, and those elements don't want any more. They don't want to give them up. They don't want any more noble gases. They don't react. But if you have less than 8, then you're going to get some reactivity out of that element. And that's what those Roman numerals stand for. If I have, say, halogens with VIIa, 7A, it has 7 electrons in its outermost shell. But for some reason, the International Union of Pure and Applied Chemists decided that they'd rather number them from left to right, 1 through 18. So you just look 1, 2, and then go down to the transition metals, 3, 4, 5, 6, all the way to 12, and then cross, which is not as helpful, I don't think, for the chemistry. But when you're filling out that table, that extra credit, 1 through 18 is the one that I asked for. I have some students put the other one in there too. That's fine. Be sure you get the 1 through 18 in there though. And then notice down the left-hand side, the periods are numbered from hydrogen 1, lithium 2, sodium 3. They're labeled down to 7 periods across. Another feature of the periodic table, and I've mentioned it earlier, but I didn't define my terms, is this dividing line, that dark black line, that stair step running between boron and aluminum starting, and then you just step down one at a time. That's the dividing line between metals on the left and non-metals on the right. And generally, the metals have certain characteristics and the non-metals have certain other characteristics that set them apart. Metals, if there's enough of them and you polish them, will have a luster, right? They'll be kind of shiny. So we use metals to make mirrors because they reflect. That's where the luster comes from. Most mirrors that you find in your bathrooms or in, my mother used to have an old one. It was round. I don't know where it is now. I think it was broken. But what they do is they have this sheet of glass and they try to make it as perfectly uniform thickness all the way through so you don't get any distortions. But on the backside, they coat it with silver. And they use a chemical reaction that is fairly common and easy to do. And then they cover that with something to keep the silver from getting scratched off. But that silver provides the reflection, the luster. Metals have very high thermal conductivity. They will conduct heat. They will also conduct electricity. And they're malleable, right? You can bend them. Pure iron, you can scratch it with your fingernail. It's only when you add a little carbon to it that it gets hard, right? Steel. But pure iron is malleable. They're also ductile. That's not on the list, but ductile is characteristic based upon the same physical property as you can stretch it into long, thin wires. Whereas non-metals, oh, by the way, most metals are solids also. There's only at room temperature. So at room temperature, there's only one metal that's a liquid. Any ideas? Make a barometer out of them. Used to make thermometers too. Mercury. Mercury is a liquid at room temperature. There's one that's really close. It's below aluminum and to the right of zinc. Ga, that's gallium. Gallium has a melting point that's below body temperature. So what's body temperature in Celsius? Anybody know? 37 degrees Celsius is body temperature. You use that formula. We covered that already. Temperature conversions, right? Use that formula. 37 is 98.6 Fahrenheit. But gallium has a melting point, I believe it's around 35. So if you put a chunk of gallium in your hand, it'll melt. But the only one that's liquid at room temperature is mercury. Rest of them are solid. Non-metals, though, they run the whole gamut. You got some gases, some solids, and some liquids. The only liquid of the non-metals is bromine. Bromine is a liquid. Iodine's a solid in that same family. Fluorine and chlorine are gases. Bromine's a liquid. Iodine's a solid. Acetine's a solid too. Carbon is a solid. Nitrogen is a gas. So you have a full range. When you have solids as nonmetals, and it's not going to, I didn't put that in there. They're usually very brittle. Right? They're not strong. Oh, there we go. Okay. So I covered the ones on the metal side. The ones on the non-metal side, they're good insulators. They don't conduct electricity or heat very well. They don't have a luster. They're kind of dull. They can be all forms, all phases of matter, and they're brittle in the solid state. They're not ductile. You cannot pull them into a thin wire. And there's your dividing line between metals and nonmetals. Now, if I haven't said this before, I'll say it again. Nature just does what it does, and we try to explain it. So by dividing things into metals and nonmetals, we're trying to explain something about their behavior. And when we draw that dark line, we're saying the right-hand side is nonmetals, the left-hand side is metals. But there's an in-between. Right along that dark line, you get silicon, germanium, arsenic, antimony, tellurium. Those elements can behave like metals in some cases and non-metals in others. Depends on the environment. We call them metalloids. And we use one of them as the foundation of our electronics industry. Any ideas which one? We named a valley after it in California. Silicon Valley, right? It's where all the high-tech companies are. Silicon is the basis of all the microchips that go into our devices, computers, calculators, cell phones, all based on silicon. Because it has characteristics that bridge the gaps between metal and non-metal. And it's cheap. You can find it in abundance. Right? Walk on any beach. You got silicon in your toes. Actually, it's silicon dioxide, but silicon. All right. So let's talk about building an atom now. Your book refers to, well, okay, let's start here. Remember the nuclear atom, Rutherford's nucleus, has protons and neutrons in it, except for hydrogen. The first isotope of hydrogen has no neutrons because it only has one proton. It doesn't need any neutrons. But now's a good time to talk about those other two scientists in that were on that first slide. Yeah. Niels Bohr. Niels Bohr said that his theory proposed that the atom looked like a planetary system. You know, like the sun at the center and the planets whirling around. The planetary model. So he said that the nucleus was like the sun and the electrons were like the planets. Right? And these go all the way around. These levels are called electron shells, and he gave them whole number integers, n. N could equal 1 or 2 or 3 or 4 whole numbers. Okay. And this would be 1, 2, 3, and on up. Okay. He said that this is the lowest energy that an electron can have in that level, in that first level. You can't get any closer to the nucleus. And in order to go out here further from the nucleus, it happens in what's called quanta. In other words, the amount of energy required to go from here to here is a fixed amount, and there's no in between. It either goes to here or to here or to here, or it goes nowhere. Okay, that's called the quantized electron. It moves in that way. So if this is the lowest amount of energy and your electron's here, that's where it would be for the hydrogen atom. It'd be right there with one proton. Okay, that's hydrogen. In fact, Bohr's model only works for hydrogen. When you put more electrons out here and protons here, then his model falls apart. But it was the beginning. So we got one proton, one electron. So what happens to that electron if you put some energy into it? And the easiest way to get energy into that electron is with a light beam. So you send light in here, right, of a certain, well, let's see. We usually designate that H nu. That's the energy that hits that electron. If it's just the right amount of energy, it'll go up to that position. If it's more and it's just the right amount, it'll go up to this one. Okay, so that's Bohr's model. It's based upon this N, which is also called the principal quantum number. Okay. The basic idea here is the closer the electron is to the nucleus, the lower its energy. Based upon the fact that in order to get it to move, you got to add energy to it. Okay? So, what if we have an excited atom of hydrogen and the electron's out here? And we let it relax. That's what we call relax. That electron goes down to here. It goes from 3 to 1. What's going to happen? Well, it goes from higher energy to lower energy, and we have to conserve energy. You can't create energy, you can't destroy it. Right. So what does it do? It emits some light. Right? That's how we know. We can see the light that comes out and measure its wavelength. And with that, we can determine how much energy it took to go from here to here. Or go from here, how much energy we get back when it goes from there to there. So it's exactly the same amount of energy to make it go from here to here, or we get it back when it goes from there to there. Exactly the same amount. Okay, so that's the principal quantum number. And that is preserved in subsequent theories. So the next person to come along was Schrodinger. And Schrodinger put a whole group of equations together. He was a mathematical genius. He put these equations together to describe the atom, and he needed more numbers, right, in order to build bigger atoms with more protons and more electrons. Right? So from this point on, we've gone beyond Bohr's model. Right? This was Bohr's model. He was a Danish person. And Schrodinger was German. So if we take each one of these, now Schrodinger's going to add another number to the sequence. to the group. We've got this number. We can have L numbers. And L is starting with 0 and whole numbers up to n minus 1. Okay. So if we have 4, we have the possibility of 0, 1, 2, and 3. Because that 3 is n minus 1. Okay. Think of this as a tree, roots. Start here, and if you go down this one, then the root can divide three times. So at each one of these, you could have so many L's. They sort of branch out from each other. This is known as the angular momentum. Quantum numbers. These are all quantum numbers. So if we were at 1, right? How many L's can we have? Well, only 1, right? Right, 1 minus 1 is 0. That's it. How about 2? We can have 0 and 1. So we can have 2 at this level, 2 L's. We can have 3 L's at this level. Okay, so forth and so on. These in your book are called subshells. So this would be, I think they called them, yeah, these are called shells in your book. These are called subshells. But when we start to build an atom with these numbers, it gets kind of messy if you only have numbers to look at. So we keep the numbers here, but we give these letters. So if we have a subshell with a 0L, we call that an S subshell. And a 1, we call it a P subshell. And a 2, we call it a D subshell. And if we have a 3, we call it an F subshell. Now we're starting to get information that will make sense of the periodic table. Because as you build atoms, you're adding electrons to these shells. Go in lowest energy first and just move out. So at some point, you may need F shells. But if you're down here and you're in, you won't have access to them anyway. And if we look at the periodic table, we can say something about what electrons are going into which shells. I'll say more about that in a minute. Let's see. I'm going to come back to that. The maximum number of electrons you can have, because right now it won't make any sense. We're going for 4 quantum numbers. We've got the N, we've got the L. Then within each one of these, you could have M sub L. This is the magnetic quantum number. And the magnetic quantum number takes any one of these and says minus L to plus L with 1 step at a time. So if it was 3, we could go minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So you could have 1, 2, 3, 4, 5, 6, 7, 8 levels inside this one. Okay, let's see, 1, 2, 3, 7 levels, excuse me, 7. 7 levels inside this L. And we got one more. The last one's easy. M sub S is the spin quantum number. The spin quantum number simply says that within each one of these, you can have 2 electrons. Inside each one of these, 2 electrons, but they have to have opposite spins. So it can either have a +1/2 or a -1/2 spin. Okay, those are all 4 of the quantum numbers that describe the atom and explain, as we build atoms, where they fit in the periodic table. Okay, so let's go back. Let's see. Okay, let's look at this too. The number of orbitals that you can have inside each one of these. And I think we're down to here. This is the orbitals. There we go. So how many of these can you have inside each one of those? In each one of these subshells, this one you can only have 1. That's it. This one you can have how many? -1, 0, +1. 3. So there it is. The P's can have 3 orbitals. The D's, 2's can have -2, -1, 0, +1, +2, 5. So you have 5 orbitals there for the D's. And the F's, we've done that one, that's 7. So how many electrons does that mean for each one? Well, if you can have 1 here, only 1 of these orbitals, and each one can have 2 electrons, that means you can have 2 electrons in each orbital for the S. For the P, you can have 3 orbitals with 2 electrons each. That means 6. Okay. For the D's, you can have 5 orbitals, 2 electrons each is 10. 10 electrons. And for the F's, you can have 7 orbitals or 14 electrons. Okay. Now, think of those electrons as you build an atom. What are you doing? The next element's going to have 1 more proton, which means 1 more electron. So the electron's got to go somewhere. It's going to go in here. All right. So if we look at the periodic table and we say, all right, which orbitals are being filled as we move along a period and then maybe circle back and start another period? Here, these 2 are only S orbitals being filled. The 0 L. So there are 2 electrons. You can have 1 and 2, and that's it. You're done. These are all S orbitals. 1 electron, 2 electrons. That's why they behave alike. They've only got 1 electron each in that outermost shell. These only have 2 electrons. And then if you move to L equals 1, or the P orbitals now can have 6 electrons. 1, 2, 3, 4, 5, 6. So you're filling the P orbitals with these. And then you can go to L equals 2, or the D orbitals, and how many can we have there? We have 5 orbitals with 2 electrons each is 10 electrons, which is 10 protons also. So we can go with these, you're filling 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So these are the S orbitals filling, these are the P orbitals filling, these are the D orbitals filling. Okay. So we got 1 left, right? F. If L equals 3, which ones fill the F orbitals? These are known as the inner transition metals. They fit right in that slot right there. Right there. We pull them out because, well, for 2 reasons. One is we don't want our periodic table to cover the whole wall. If you slide them in there, you've got to stretch your table out. But if you pull them out, that makes the table more compact, but it also identifies these as F orbitals filling. So F has 7 with 2 electrons each is 14. Right? 2, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Start here, excuse me. These are transition metals. These are the inner transitions. So there are 14 of them there in that group. You're filling the L's with 14 electrons, or as you build the atom, that means 14 protons too. One at a time, and you get a new element each time you add a proton. Okay. So I'm not going to go back to that other table because I already told you that stuff. Now, these numbers have a general meaning to them. Let me move this out. Originally, Bohr used these numbers to calculate the energies of the electrons in those shells. And we still think of them in those terms. These numbers refer to the energy of the electron. Okay. The angular momentum, excuse me, refers to the shape of the orbital. So on this slide, we see that those that are S subshells are spherical. Now, they're not a solid sphere, right? For this one, yeah, it's a solid sphere. For that one, it's like a sphere and then a shell of a spherical shape around it with dead space in between. But this refers to the shape. The p orbitals are kind of like dumbbells, and so are the d orbitals. But the d orbitals are not only dumbbells. They've got some orbitals in there that are donut shaped. And then the f orbitals are even more complex. But this subshell, the number refers to the shape. Now, do we know that they look like this? Can't see them, right? We've never imaged these orbitals, or these subshells. These are mathematical predictions. Right? This is what we think they look like. And this, when we get to, this is what we've been discussing so far. Is quantum mechanics. At this level, this subatomic level, we can no longer be secure in our calculations. We have to think of what's going on down there in the atom in probability terms. What's most likely to happen? What's most likely to be the shape? And what we're doing with these representations of these orbitals is we're saying this is where the electrons are most likely to be found. Let's see. 1 second. Let's see if I've got if I'm going to use. I don't see it. Okay, it's not in the slide, so I'm going to write it on the board. There was another physicist, mathematician. His name was Werner Heisenberg. What Heisenberg said was that at this level, actually, his equation, and I'm not going to bore you with the equation, his equation said that everything in the universe will fit his description. And it says that you can't know, well, you could know both the momentum and position of an object. If the object is large, like us, like my body, you can tell how fast I'm moving if I'm walking or if I'm riding in my car and where I am at any time. That's because I'm so big. So it has to do with the size of the object. But when you get down really, really small, like these electrons, you can't know both of them. And momentum, oh, you haven't had physics. Okay. Momentum is mass times velocity. Right? And since the mass doesn't change, we're interested in the velocity. So at this level, you can't know both how fast the thing is moving and where it is. And fast refers to energy. So what are we going to do? Sometimes we want to know where it is, sort of, but most of the time we'd rather know energy. That's more important. So when we know the energy and we're satisfied with the speed and the energy of the electron, we say, okay, it's got that energy and it's going to be somewhere in this space. That's what this representation is. The electron's going to be somewhere in that space. 99% probability, right? It could be someplace else, but we're not as interested in that as we are in this. Okay. I need to get a move on. I'm going to run out of time. But we don't, our lab today is finishing up the graphing techniques. Yeah. So you can turn it in next week. So I've got a little bit of time. I can bleed over into the lab a little bit. So that's what these shapes represent. And let's see, energy, shape. This is orientation. So the M sub L, or the orbitals, are represented by orientation. And the best example to understand orientation is to look at the p orbitals. These right here, where L equals 1, you have p, and you can have three possibilities, right? 1, -1, 0, +1. On a three-dimensional scale, like this line is in and out of the board. So this is X, and this is Y, and this is Z. So one of those, the -1s, for instance, would look like this. The zeros would look like this, and the +1s would look like this. So each one of those p orbitals have a different orientation based upon this number, -1, 0, or +1. That's orientation in space. And the last one is a no-brainer. This is just, I don't think it has a name. You can put two electrons together in an orbital, but they have to have opposite spins. Just think of them as rotating globes, planets. They can't both be rotating the same way. Got to be rotating opposite to one another. All right, so there's your orientation for the p orbitals. And there's your spin. You have to have opposite spins. All right, so as we're building elements, as we're building the atoms of an element, we have to observe these rules. And these rules were invented not to make life difficult, but to keep us from making mistakes. The Aufbau principle. That's a German word. I don't know what it means. I think of it in terms of the Aufbau principle says, do it this way. And this way means when you add electrons, as you add electrons into your you're moving through the periodic table, one proton at a time, adding one electron at a time along with it. The electrons go into the next highest energy level. You go from lowest to highest until you've satisfied conditions for filling that orbital, and then you keep moving up. That's all that means. You start from lowest, go to highest. The second one, Hund's rule. When you go from here to here, let's use p orbitals. Right? If the L equals 1, then you have p orbitals. Well, the m sub L then is going to be -1, 0, and +1. What Hund's rule says is, as you're building your atom and you're adding electrons in, at this level, if you're going, say your atom needs an electron in this level, all right, it goes there. If it needs another one, so you go to the next element, you're adding a proton and an electron, the next one has to go over here. You can't pair them up until this orbital has at least one upspin in each of its subshells. In each of its orbitals, excuse me. This is a subshell, and this is an orbital. So each orbital has to have at least one electron in it. So we go, the next proton and electron, we go there. Then if we need another one, now we can go back and start pairing them up. That's Hund's rule. They have to all be unpaired until you get one in each. Then you can go back and pair them up as you're building. Then there's the Pauli exclusion principle. No more than 2 electrons may exist in a given orbital. Actually, that's a simplification. Pauli exclusion principle says that no electron can have exactly the same set of 4 quantum numbers. So if you've got one that has n equals 2, and then subshell is 2, and orbital is 1, then those electrons can have these numbers the same, but down here, it either has to be 1/2 or -1/2. There has to be, they can be different anywhere, but the same set of 4 quantum numbers has to be unique for every electron. That's the Pauli exclusion principle. Okay. Here's the fly in the ointment. As we're building atoms, we're making them bigger and bigger and bigger with more protons, more electrons. As you get more protons in the nucleus, and especially more electrons out here, they start to interact. Right? The electrons don't have the luxury of neutrons to stabilize them like the protons do in the nucleus. So sometimes as you're building higher and higher energy, you get some inversions. What you would normally think as the next highest energy is actually lower than the one you're in. And that's what we see here with these overlaps here. Right? In this case, 5s is lower energy than 4d. We would expect the 5, because 5 quantum number says energy, it should be higher energy, but it's not. Or here, this 4s is lower energy than 3d. They call it shell overlap. That's okay. So we also need a method to help us put electrons in the next lowest orbital, because the Aufbau principle says they have to go into the next highest energy level. Okay, so here's how we do it. If you don't have the periodic table, then this is how it works. And I should give you some orientation also. I'll leave that there. When we write the electronic configuration of an element, we're going to use these 1s and these letters. Right? So the very lowest one is what? 1. N equals 1. Right? So the lowest subshell, L, that you can have from that 1 is S. And that's it. Right? You got to go to 2 to get more. So the next one is N equals 2. And it can also have an S, but it can have a P also. Right? Because with 2, you can have a 0 and a 1. So there's the 0 and there's the 1. If we go to 3, now we can have an S, we can have a P, and we can have a D. Okay, so that's the form that we're going to use. The N number here and the L letter here. Now we know that when we get to P, this could have 3 orbitals in it, and this could have 5 orbitals in it. Right? So we only use those if we need them. All right. So I said that so that this would make more sense. If we draw these out and we say, all right, so we can have 1S, that's it. The next level, we can have 2S and 2P. The next, we can have 3S, 3P, 3D. The next, we can have S, P, D, and F. And then 5, we can have S, P, D. Yeah, we'll put an F there. Theoretically, we could go up to G, but there are no elements that need G, not at the, my mind's gone blank. Not their lowest energy state, ground state. Ground state atoms, you only need Fs. If you're going to push the electrons up with some energy into higher orbitals, then you can go to Gs, and I think there's an H. But we're not worried with that. We're just ground state atoms. Okay, then you go 6. Let's see, how we doing? We're only going to go up here. 6P, 6D, and then 7S, 7P. That's good enough. Okay, so these are the possibilities for each one of these principal quantum numbers, shells and subshells. And if we're going to fill them in order of lowest energy to highest energy, we use the diagonal. So if we draw a diagonal here, we can fill that one. Then we go back, fill that one. We go back, fill that one, and then this one, and then go back and fill that one and that one. And then now we got to 4S. We're not going to go to 4P because we got to get this 3D. There we go. So now we go to 4S, 3D, 4P, 5S. Then we go back to 4D, 5P, 6S. And then we go back to F. There. There. So that diagonal process will keep you in order of energy. Now, I know that's a lot of trouble. There's an easier way. After saying all that, there's an easier way to do it. Use the periodic table. Oops, excuse me. Electron configuration. This simply takes an element and puts the electrons in their places at lowest energy to highest energy and fills that structure. So for nitrogen, we would start off like this. We'd say nitrogen has how many protons? Let's see, 7. Right? We don't have to put neutrons in there because they have no impact on the electrons. Just write it that way. All right, from lowest to highest, 1S, 2S, 2P, 3S, 3P. We may not need all of them. So how many can S's have? Just two, right? Just that one with two electrons, opposite spins. So we can put two in there. We got five more. Okay, we can put two in there. So that's four. We got three more. How many can P's hold? Three orbitals with two each is six. Okay. So we only need three more. That's it. That's nitrogen. Okay, that's the electronic configuration for ground state nitrogen. Now, what would the orbitals look like for this one? Okay, if we subdivided those orbitals, right, P's can have three. We would put them in like that, like that, like that. That's the way they would go in according to Hund's rule. But you only do that if you need it. Right. This is the electronic configuration for nitrogen. That should be up right here. There we go. We call it the condensed notation. Now, the authors, the creators of these slides, they like boxes and double-headed arrows. I don't. It takes too much trouble. So I just put a line for each orbital and then half arrows, one up, one down if we need it. But that's what it would look like for nitrogen. How about sulfur? Let's do sulfur. Can you find sulfur? How many protons does it have? 16. Yep. That means 16 electrons. So if we go 1s, 2s, 2p, 3s, 3p, maybe we need more, but let's see if we do. So this S's can have 2, 2, 6. So that's 10. We got 6 more. Now we need 4 more. Okay, let's count them up. Let's see, 2, 4, 6, 10, 16. There we go. That would be the electronic configuration for sulfur. Notice what I said earlier about which ones are filling. Let me get my stick. This is the 1s. This is the 2s. That's the 2p. This is the 3s. This is the 3p. 1, 2, 3, 4. So 3p, 4 gives you sulfur. That's the last orbital in the group. And if you know how the table is set up, you know that you've got to have a 1s2, a 2s2, a 2p6, a 3s2, and a 3p fourth. So you can use the periodic table to draw the electronic configuration. Did I lose somebody? Takes practice. That review document I gave you should give you some practice. Okay, the next one is a monster. Barium. Where's barium? Look on the left-hand side, way down toward the bottom. Yeah, barium's got 56. Okay. I'm going to show you a shortened version. I'm going to show you the long hand, and then I'm going to shorten it, so it'll make it easier to draw the configuration. Okay. So this will be 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. Let's see. 3p, 4s, 3D, E, 5S, 4D, 5P, 6S. I'll have to erase some of these. And that should get it. Okay, so 56. Right, we know S's have 2s, 2, 6s for P's, 2, 6, 2. How many for D's? 5 orbitals with 2 each is 10. Then 6, then 2. Let's see, how many do we have so far? 2, 2, 4, 10. There's another 10, that's 20. Another 10, that's 30. We got 8, so 38. And we need 24. No, 14. So there's 10. And there's 6. No, more than that. 18. Sorry, that's right. So that should be it. Let's count them up. 2, 4, 10. 2, 4, 10. And that's 30. There's 10. There's 8. There's 8. So that's 40, 56. That's it. So that's the complete ionic configuration of barium. Now, notice what we did in the process to get to here. We went down each row, right? And when we got to this one, 4S, these are 3Ds. So this period 4 has 4 S's, but then when you get to the D's, you back up 1. So those are 3Ds. Then you go back up to 4 P's. Now you're in period 5 S's, 4 D's, and then back up to 5 P's. Now you're in 6 S's. So barium is going to have 6S2 on the very tail end. But if we can condense it further, notice that as you back up and you come to a noble gas, noble gases are complete. All their shells are full. So if we say xenon 54 as the root, xenon 54, then all we have left is 6S2. So barium can be viewed as an electronic configuration of xenon plus 6S2. Okay, that's the, let's see, they called it the condensed notation. This is the condensed, this is the ultra condensed. There we go. Or shorthand. Okay, that we can simplify. What I won't be doing to you is giving you any of the inner transition metals, the F orbitals, because they're kind of squirrely. Even though we follow the process and we say, all right, so many electrons here, here, and here, sometimes there's reversal. And in fact, even in some of the d orbitals, they do that. We would write out, say, for copper. Copper would have 3D9, but it's already got 4 S's here, 4S2, 3D9, but it's not. The lowest energy form for copper is 3D10, 4S1. Okay, so that's one of the anomalies. And I don't think in this course we need to deal with those. Right. I could spring one of those on my other class. The 2-semester version. I think this is enough. So what's the electronic configuration for sodium? Well, sodium has how many? 11, right? Okay, let's look at the periodic table and say, all right, so the sodium is going to be 1s, 2 for hydrogen and helium, and then 2s2 for lithium and beryllium, and then 2p6 for boron, carbon, nitrogen, oxygen, fluorine, and neon. And then we swing around to sodium's period, 3s1. 2 plus 2 is 4, 6, 11. There you go. And we did it from the periodic table. Okay. Let's see. Am I getting close? Yeah, sort of. Actually, the next couple of slides I've already talked about, so we don't have to spend a lot of time on it. So one thing to bring out of all of this is for each of the groups, the families, the outermost orbital or the outermost shell, the outermost shell looks like the one above it. That's what makes their chemical behavior similar. Those outer electrons are similar, not exactly the same, but similar to their neighbors in that group. That's why they have similar chemical behavior. And those we call the valence electrons. Right? Those are all group ones. Notice that 2s1, 3s1, 4s1. That's why that when we, let's see, we've named compounds yet, have we? We haven't named them yet, right? Okay. When we get there, you'll need to know what is the charge on the ion when it's in an ionic compound. And for lithium, sodium, potassium, it's always a +1 because they'd like to get rid of that one electron, each one of them. What would that do? Well, notice what happens when you get rid of one electron from that first group and back up to the number of electrons you got left. Looks like a noble gas. It's like everybody's trying, in a chemical reaction, everybody's trying to look like a noble gas, electronically speaking. Those are the valence electrons. All the electrons in the highest orbital. Excuse me, the highest shell. Okay, get my terminology straight. Okay, so we went over this before. In these areas, there are orbitals that are being filled, right? The first two columns on the left, s orbitals are filling. Last 6 on the right are the p orbitals filling. Transition metals in the middle are the d orbitals filling. And I mentioned that the lanthanides and the actinides in that bottom 2 rows, those are f orbitals. Okay, the distinguishing electron. I'm not sure what your authors are trying to do there. Okay, the last electron added to the configuration of an element is the distinguishing electron, and it's always an increasing energy. That's redundant. That's what the Hund's rule says. Excuse me, Aufbau principle tells you that. Valence electrons. So that connects the dots for Doberanier's triads. No, Meyer's valence. When he mentioned valence, he at that time didn't make the connection between these outer electrons and his terminology, but we kept the term, and now we apply it to those outermost electrons. Okay, so those are your groups. The 2 columns on the left and the 6 on the right are often referred to as representative elements. Don't ask me why. It doesn't make any sense to me either. But if any of your other courses reference octets, what they're talking about is, let me use my pointer. What they're talking about is these 2 columns here and these 6 columns. So in any one of these, 1, 2, 3, 4, 5, 6, 7, 8 electrons in the outermost shell is an octet. That works for the second and the third period really well. But once you get down into the 4th period and you're crossing over the transition metals, it's not quite as useful. But most of the interesting biochemistry that happens, the living systems, are going to happen with the first 3 periods anyway. So that's why the octet is still used. One of the reasons. Okay, elements in group 1 and 2 are referred to as S-area elements. Right? Those first 2 columns. Oh, we must be getting close to the end. Concept questions. Okay, we have 2 elements. One is a gas and the other is a solid. Okay, what does that tell you? First of all, if you got 2 elements like this, solid, this one is a nonmetal. Can't be anything else. This one could be either. Okay. Each contain identical number of electrons in their outer shell. That means they're both in the same family. So we're saying same group. Both of them, same group. So if this is a nonmetal, and this could be one or the other, then you need a group that crosses that line between metals and nonmetals, right? It could be the boron group, carbon, nitrogen, or oxygen, right? It can't be halogens because you go all the way down to halogens, you're still nonmetals. So it's one of those 4 groups right in there. All right. So let's see. Let's use 13, 14, 15, 16. So it's 13, 14, 15, or 16. One of those. It's like being a detective. These elements are, and it gives you the answers. Oh, okay. Never mind. I see. All right. So knowing what we know so far, the first one, fluorine and iodine, it can't be that one, right? Because you're not transitioning from solid to gas. Well, gas to solid. Okay, never mind. It could be because solids and gas, they could both be nonmetals. It could be metal or non-metal. Oh, in that case, it could be 17. Okay, I imposed metal, non-metal on it, right? They could both be non-metals. That's possible. So fluorine is a gas and the iodine is a solid. That's possible. A is possible. Nitrogen is a gas, sulfur is a solid. Oxygen is a gas, sulfur is a solid. Okay, so it could be any one of those. So we have to go to our second level. Contain how many neutrons each? So fluorine contains how many neutrons? Right? It's 19. Fluorine would be 9, and 19 is the most common isotope. That's possible. 10 neutrons. Right? How about iodine? Can it have 74? Well, let's see. Iodine is 53, and most common is 127. Nope, can't be that one. Now, how do I know the most common isotope is 127? Look at the atomic mass and what's it closest to? Right, round up or round down? It's closest to 127, right? So that means most of the isotopes of iodine are close to 127, right? So A is out. A is out. How about nitrogen 14 neutrons? Nitrogen is 7 and 14. No, the 14 is total protons and neutrons. It'd be 7 neutrons, right? So the second one's out. Process of elimination. Oxygen. Oxygen is 8 and 16, right? Right? That's not the number of neutrons, that's the total, right? So that's wrong too. How about the last one? Fluorine and iodine. Wait a minute. They contain blank, blank neutrons respectively. Now, why is it the first one? That's right. 74 neutrons. Oh, you guys didn't say anything. It's 53 with 74 neutrons. Could have saved a lot of time if you'd caught me. All right. Do I want to mess with the second one? After my track record's not too good today. Let's skip that one. Okay, that's chapter 3.